Look at the kitty cats over here, over there, and over here. I was just telling Fuji Baba, Baji Baba, and Suji Mama, and Mama loves you. They were being a little bit bad and they wanted attention. So I said, Mama loves you, Mama loves you, Mama loves you more than the universe. And we will be discussing the universe here on the live today. So here we are, kitty cats, me, you, and Cosmology universe. By the way, I should mention, look at my new earrings. These are from Shop Mart. Sorry, not Shop Mart, Spot Mart. I'm so sorry. I am still used to saying these sponsor names. This live today is gonna be sponsored by this store called Spot Mart. Small decoration, big style. I'm so sorry I mispronounced it the first time. Let me just read out to you the name of the exact earrings. Spot Mart gold earrings for women, chunky gold plated earrings, statement earrings. So anyway, sorry about that, and thank you so much for listening to who the sponsor is of this live stream. So here we are. We are live. Good evening, good morning. Hi, Lee, how are you? OMG, hi. Yes, we're back, and this is the main amazing physics night live. This is what got the physics lives started. I made like physics Fridays because most of my, I was going live with the kitty cats a lot, but this is our OG Physics Friday live, and we're going to be talking about cosmology in just a little bit. I just showed the kitty cats, Baji, Suji, Fuji. They were actually making some trouble, but I told them that they are more important than the whole universe. Thank you, God. Thank you, universe. We are going to get started. Leke Prabhu ka naam, as people say in Hindi. And we're going to make sure that we can share this live. Why did I do that? I changed the brightness instead of the volume. You're good. Yay. Welcome, everybody. I know my face is, the other way on the live because I'm using the front camera selfie mode situation, and I'll have to see how that affects all the things I write and stuff too. But here we are. Hello Lee, hi. Hello Pokemon. Okay, so here we are. Let me make sure I can share the live with everybody. I just got these earrings in the mail from Spot Mart. That's the name of the store. And I'm supposed to announce at the beginning of the live that, these earrings are the sponsor of the live, and they have sent me these earrings. Thank you so much, Spot Mart. Thank you for the kindness and the earrings, and for sponsoring. Tonight, we will have so much fun indeed. We will talk about physics. We have the kitty cats here. We are all here. Oh, and I'm wearing a holiday party themed sweater. So I'm very, very excited. So think of this as a corporate holiday party, except more fun. So we're going to be talking about our favorite things in the world and this universe indeed, which is, of course, physics, cosmology, astronomy, astrophysics, and cats. And you're here, I'm here, Baji is here, he's over here, and we will get started as soon as I share my live. So today we will talk about cosmology as a whole, but we will focus a little bit on Big Bang nucleosynthesis. So that's what I put in the title. We are live. Join us. Join us. Thank you for coming in. Welcome to the live. We will stay. Yes, this is me. Live for Doro. Hi. Yes, this is me. How are you? Live for Doro. Is that Doro? I know I see your username. Sometimes it changes. For some people, could have changed. It is changed my name. Okay, yeah. I have a pity. I have a pretty good memory. So I tend to remember the people who are, who join and such. So yeah, please do come in. Welcome to the live. Welcome, welcome, and come on in and let's get started. We will talk about physics. I will share the live again. Just, you know, doing my due diligence here to make sure that people know that we are live. Give me 1 second. And then we will get started. So we have been talking about specifically the smooth early universe. Oh, Fuji. Fuji, look, Fuji has his toy now. Fuji likes to bring me his toy. See that little blue toy? That's the toy that he brings me every night. Thank you, God. Thank you so much. Thank you, Fuji. Debi, come. You want to give me your toy? That's his favorite toy that he hunts for me and brings to me every night. Oh, I'm so grateful. So, thank you for being here. Join us and chat. So whenever you come in, feel free to join and feel free to send any chat messages. I will read them. Pretty much I read and announce all of you guys with your usernames, and I shout out all the people who are making the comments in the chat as well. Thank you already to everybody who is already here. And thank you for joining. So let me summarize a little bit what we have been talking about. So this is the famous Physics Friday Live. And so I should mention that for pretty much we go live almost every day now. Apologies, last night's live, we kept it more casual. I was very tired and I wanted to save all my energy, social battery, and voice for this live. So hopefully lots of people get to kind of enjoy that today. And yesterday we made some noodles and I thought that was fun too. We got to have a little bit of a chat, teet-a-teet with everybody who joined and kind of catch up. But tonight we're gonna cover a bunch of topics here, and I will also summarize for you what we have been talking about. So if you're here in the live, thank you so much. Welcome. And thank you for being here. And if you want to say hi in the chat, then feel free. And that's how I'll know that, you're here, you're ready. And I can shout out your username and any chat messages that you send. So let me summarize what we have been talking about. So first, let me just say that we're very thankful you're here. We started doing this Physics Friday Night Lives. We've covered the entire almost 20th century type of physics. That is the last century, the 1900s type of physics. I'm ready. Yay, Lee, yay. Thank you. So we particularly paid attention to special theory of relativity, general theory of relativity, quantum mechanics, photoelectric effect, those types of things. We especially covered 1905 and sort of the 1910s, 1920s, 1930s in a lot of detail up until the World War II stuff, and how also science kind of changed during that war, and atomic bomb stuff started to happen and people started to work on that, and there were various efforts in the various countries, and different scientists even moved to different countries based on what kind of happened back then. For example, Schrodinger, somebody who was heavily involved with quantum mechanics, had moved to England and Ireland, and Einstein, of course, moved to the US. He moved to New Jersey, to Princeton, actually. And he thought that Princeton was a nice little quaint village where he had not too many distractions and he could just focus on his grand unified theory. Because at this time, by the time he's coming to the US, he's really interested in, I know at that time, most scientists were pretty much involved in, getting ready for World War II and doing the work on the atomic bomb and things like that. And he was kind of involved sort of in a secondary kind of way, not super directly, but of course his E equals mc squared was of course part of the atomic bomb. But he wasn't actually directly involved. The Americans actually did not fully trust him yet because he was a new immigrant and he was thought to be very radical and very diverse. He had lived in different places. He was, of course, more of a foreigner than some other people might have been at that time. So he wasn't actually involved in the super duper hush hush research for the atomic bomb, but of course his fundamental physics was involved in that, in the making of that particular warfare technology. So we talked a lot about the 1900s, especially the earlier half of the 1900s in my previous live streams. And if you're interested later on, if you want to catch up with these types of discussions, we kind of discussed at length Einstein's work, quantum mechanics, Niels Bohr, all of these types of people and their different discoveries in the 20th century, and really the paradigm shifts that happened during that century, especially with the discoveries in quantum mechanics and, the hydrogen atom, the fact that there is a nucleus, the fact that even within the nucleus, there's the proton, but then there's also the neutron. So, hydrogen atom doesn't have a neutron, but later on they were like, oh my gosh, there's also another type of particle sometimes in the atom, which is the neutron. So the neutron was discovered as well afterwards. And, looking at sort of these small scale type of physics and effects and the entire birth of quantum mechanics and the fact that you need a probabilistic type of dynamics to describe the science of the very small, when you're sort of at the atomic or the electron level, when you write down the wave equation of a particle, which is what Schrodinger gave to us, we found, actually Max Born said, that it is not, the wave equation does not give us the position of the electron, but the probability of finding that electron. And then a lot of people were very, hi Harley, hello. A lot of people were pretty upset about this in the sense that they were not used to mechanics being probabilistic. When you, oh, hi Fuji. Fuji's looking at me and blinking. So I wanted to acknowledge his kisses. Hi baby, hi Fuji baby. So people were not used to the answer to something, such as the position as a function of time, to be something probabilistic. For the longest time, especially something like Newtonian mechanics or classical mechanics, the mechanics that describe, say, the moon, the sun, the comets, things like that, the mechanics of those types of things. If I gave you the position of the moon today, you could probably predict it for me for the next 1,000 years or something. So NASA still uses these equations even now to describe the mechanics of classical objects. But now we were talking about the physics of the very small, or quantum. And in quantum mechanics, people were, they were sort of a little bit unhinged by the fact that you got probabilistic answers now, and it came with uncertainty. So there was a big hurdle with that they had to, the quantum people had to kind of get through. So we talk a lot about this time and sort of the stories of that time and the politics of that time, and we have covered all of this. I wanted to let you know, especially by referencing this book called Einstein's Cosmos by Michio Kaku. So if you want to catch this type of thing, you can go and look at our previous live streams. I'm kind of mentioning all of this as a summary now, so bear with me. But then we basically started to also discuss, okay, so we talked about the very, 20th century, the very modern physics, but more in the 20th century, right? So because all of the things that I've just now kind of described, relativity, quantum mechanics, and, atomic bomb, all of this stuff is basically under modern physics. Radioactivity, this is all under, say, if you took a class as an undergrad in physics, or just any undergrad, if you took the modern physics class, this is sort of what the topics that you would probably cover. But really, by modern physics, it's really that 20th century timeline that you're covering mainly in this part. So coming to a little bit more recent time, what is of the most hi Mac tonight. What is of more what's the word? What is of more relevance today? What is happening now? What are the more current topics that basically we research today in physics and astronomy and astrophysics? Those are something that we have started to discuss now going forward. So our more recent lives, perhaps sort of starting towards the later part of November maybe, is where you might find this type of more recent topics. So just kind of giving you an orientation of what you might find where. And we started to really talk about the biggest open questions of the universe at this time, which is number one, what is dark energy? And number two, what is dark matter? So because you will see, we will talk about it from a cosmology perspective, you will see that these ingredients of the universe are actually very important. They actually form the majority of the universe. And turns out we don't really know exactly what they are. Hi. Okay. Hi, Thomas. Here from Armaga. Hello. So we even though something like dark energy, the concept of it was discovered over 100 years ago, and really it was discovered in the sense that it was written down almost reluctantly by Einstein when he was working on his equations for general relativity to describe the universe. He realized, just like people before him, such as Newton, that when you write down the equations for the universe and you're thinking about gravitation, and you also realize that the universe is not collapsing on itself, there must be something that is kind of pushing things out as well, because gravity is an attractive quality. It might make things collapse. So then he basically wrote down a placeholder in his equations and called it the cosmological constant. Hi, Islam Yogabov. Hi, how are you? Thank you for the emojis. So this is when this cosmological constant concept was first introduced. And over 100 years later, we see that this is actually related to the dark energy concept. And we still don't quite know what dark energy is. So that is what something that we will also discuss in this live. We will now start to sort of tackle the topics that are more of today. In other words, we will be talking about, click the link. Okay. Thank you for coming to the live, Dr. CS. How are you? So we will be talking about more of the more current topics at this time. So anyway, it's all, everybody's welcome. Hello. So live for Doro. Doro, are you kind of seeing and hearing me okay? Like, are things kind of making sense? I know we don't have a lot of people in the live right now, which is a bummer, but I appreciate a little bit of feedback from you, if you will. Just making sure that I'm making sense. You can hear me okay and everything like that. Thank you. Oh, Groove Toot, hi. Yay, Live for Doro said, yep, making sense. I'm listening and chilling. Thank you so much. And we see you and hear you well. Thank you. Peter, hi. I just got here. I'm with you now. Okay, good. Because it's been a little bit quiet and strange. So I'm really appreciating everybody who is listening and the physics stuff and chilling. Yeah, if you need to chill and do things in the background, I just really appreciate you being here because it does help. This is going to be on cosmology. We're going to do so I'm still summarizing for the longest time, but we're going to get into Big Bang nucleosynthesis in just a little bit. So it's going to be, overall, it's going to be on cosmology. So yeah, thank you, Live for Doro. Thank you, Groove Toot. Thank you, Peter Burns. And thank you again, Groove Toot. So we're going to cover cosmology. So basically, in short, we're going to be talking for a few lives now. We have been talking about more current physics topics as opposed to the 20th century stuff that we already covered. And number one open question, just overall in physics right now, in the field of physics, in the world, in this universe, is what is dark energy? I wanted to mention that this topic is not exactly new in the sense of how it was introduced already by Einstein over 100 years ago. So in that sense, it's not exactly new, but the deeper insight that we have on dark energy, the fact that we have evidence that you need dark energy, that's actually the cosmological model that fits better with the evidence at this point in time, that that type of thing is a little bit more modern, as in it was done in the later 20th century, like 1980s, 1990s, and even now. Hi, Gray. My crush really likes physics. What's one cool fact I can tell her that will impress her? Well, you have to stay with us for 4 hours because we will be covering all kinds of cool things for the next many hours here. So thank you so much and welcome to the live, Gray. So basically, this fact that dark energy is something we need, that the cosmological models need dark energy, this is more recent. So more recent work, more current work that is in the 20 years or so, or the 30 years or so from where we are right now, is going to be sort of our topic for this live, for going forward here. But the concept that you might need something that is sort of an anti-gravity type of thing, that's not new. The other thing is, of course, so that was the number one open question of the universe, dark energy. We don't know exactly what it is. People are researching what it is. So dark energy, number one open question. Number two open question, biggest open question of the universe is dark matter. What is dark matter? This is another concept that we realize, another ingredient of the universe that we realize is very important. And we also don't know what dark matter is. So those are the two open questions, and we will talk about both in this live. My wife took the kids. Luckily for me and my neighbors, I never liked my kids. Glad they're gone. Okay, hi Disco David, how are you? So now that we kind of talked about our summary, let's just recap that. Remember, the cosmic inventory is something we've talked about on these lives. For a few lives now, we've been covering cosmology. Except yesterday. Yesterday we covered noodles, as in the noodles that you eat, and that was about it. I was kind of tired and we just chit-chatted. But other than that, most lives we've been covering cosmology, the ingredients of the universe, what makes up this great universe that we are a part of. In fact, we have been kind of talking mostly about the smooth expanding universe, as in we haven't delved too much into perturbations around the smooth universe. There are certain more details that we mean to get to, but to begin with, we're talking about the smooth universe, and also sort of the evolution of the universe from the Big Bang to sort of an early universe time era to later universe to now. And we also realized that the universe after the Big Bang, it was very hot, very dense, very excitable, and very radiation dominated. Basically, photons or light or light particles were sort of the king of the jungle back then, the early universe. Things like atoms and hydrogen atoms even could not really form very easily or stay stable. Even if they did get formed, they would get hit with a photon and become excited, and they wouldn't be able to kind of come to be for long. So in other words, we call that the radiation dominated universe in the early universe. And we actually also saw that there's this thing called scale factor. We introduced it. Let me read this part from the book. It is convenient to describe this effect, which is the expansion of the universe, by introducing the scale factor small a, whose present value is set to 1. At earlier times, small a was smaller than it is today. So basically, we introduced this concept of a scale factor to capture that basically the universe has been expanding, and to capture sort of how it's expanding. That's a troll. He was here. Okay. Okay, it's fine. You can say non-physics things too. If it's interesting, I'm sure other people would enjoy it. But basically, there's this grid that I showed earlier. You can kind of see here where the boxes are going from smaller to larger. It's almost like this co-moving distance might be staying the same between two things, but the physical distance between them is increasing as the universe evolves and expands. So turns out the universe is expanding. It's not just staying stable against gravity, it's expanding. And turns out that this expansion is actually accelerating. This is something that we've confirmed later on in the 20th century, sort of in the 1980s, 1990s, but it is a thing, and it is something that we have to deal with now, and we have to understand why and all that stuff. And that is sort of the topic of dark energy. But for now, we're just defining a few things. Basically, so we have scale factor. This helps us to understand and kind of quantify the expansion of the universe. We also have this small time t. This is cosmic time. This is another thing that we have talked about. And the scale factor's dependency on cosmic time actually changes depending on the epoch or the era of the universe that you're talking about. So the early universe, as I was mentioning in just a bit ago, was radiation dominated. It was photons mainly doing things, being hot, dense, too much excitement. And back then, the scale factor was going as t to the 1/2. So as a function of time, the way it depended on time was t to the 1/2. Later, when the universe became more radiation dominated, more matter dominated, so it was radiation dominated, when it became more matter dominated, the scale factor's dependency actually started to go as t to the 2/3. Hi, Birdie. Hi, Life for Doro again. Hi, Gray. Oh, hi. McDonald's. Good. Yeah. So the scale the scale factor is something it's given with the symbol small a. So just remember, we actually covered a bunch of math with it as well. It's something, it's a basic concept of the universe, which will be useful to keep in mind as we go forward. Because so remember, I think it was a couple of lives ago that we discussed all the, sorry, something's in my mouth, all the basic math of the universe and cosmology. And we went through these concepts. So I'm quickly summarizing that as well. So scale factor, you need that as a quantification of the expansion of the universe. Cosmic time, small t, is of course the time, cosmic time at the time that evolves as the universe has evolved. And then there's also something called Hubble rate. So this is sometimes another way of saying things. So sometimes it's good to know these concepts, just know it once, so that when we talk about it again, you'll know what we talked about. Hubble rate is basically a measure of how, so I have the notes on this. Hubble rate is basically the measure of how rapidly the scale factor changes. So what is that? Hubble rate is basically dA dt, so the derivative of the scale factor as a function of time over a. So it's really dA dt over a, all over a. So you can see, and then we usually use the subscript 0 to denote that the value of the quantity is for today. So if I say Hubble rate, that's just h. That's given by capital H. But if I say h naught, that means the Hubble rate today. Thanks for clarification. Thank you, Gray. Thank you for being here. Hi, Annie Frank. I take ducks. Ooh, you have 5 ducks. Okay. Oh, how nice. So, more generally, the evolution of the scale factor is determined by the Friedmann equation. So this is something that we covered in a lot of detail earlier, in an earlier live, in a couple of lives ago. But basically, we even have an expression that basically gives us this Hubble rate as a function of the scale factor, and in fact, as a function of the scale factor, and then it breaks down to basically the energy density. We can write down all of this in terms of the energy density of the universe, and this is the energy density of the universe that captures all of its ingredients, not just the energy of one ingredient, for example. So we kind of went through, so yes, h of t, or h squared of t, is equal to 8 pi g over 3 times rho of t plus some more stuff with rho and then a squared, where rho of t is the energy density in the universe as a function of time, where rho naught is the present value. So all of this why I'm talking about the energy density, the Hubble rate. These are the basic concepts of cosmology that can kind of come up again and again and again. So it's good to kind of have the basic, and that's why I'm kind of repeating it too. And then critical density is 3h naught squared over 8 pi g. Basically, you can write down for part of the equation that is given by the Hubble rate. If you take part of it and just equate it to the critical density, you actually get a certain value out. It's a constant, and it's 3h naught squared over 8 pi g. So these are the basic things. The critical density is very important. It's basically, you know, it depends on h naught, which is the Hubble rate today. And then once again, the energy density of the universe. When someone says that, they mean all the ingredients of the universe, not just one type of ingredient. And in these equations, the capital G generally stands for Newton's gravitation constant. So that's another thing. Sometimes we might have a capital G. If it stands for Einstein's tensor, then I'll let you know. But otherwise, when I say capital G, it generally means Newton's gravitation constant. Now, those were just some maths that I wanted to mention here so that you know what we covered in a couple of lives ago. It's not going to be super important that you understand and get all of this for this particular live, but say if you're interested in understanding what is the basic equations of the universe and all that stuff, and how do you know what are the concepts, then we've covered it in a previous live. So things like scale factor, cosmic time, Hubble rate, critical density, energy density, the metric, the geodesic, Einstein's tensor, the energy momentum tensor, and Ricci tensor and Ricci scalar. These are things that we have covered in a previous live. So if you are interested and want to kind of follow how these come to be, we've done it a couple lives ago. Okay, so now Einstein's tensor, of course, as you know, Einstein's general relativity is the more updated, correct theory. It's not, some people might not consider it completely complete because we still don't understand dark energy, but it is the more complete and updated theory of gravitation, where he includes gravitation as part of the curvature of space-time. It's kind of intrinsic in space-time. And also, Einstein's equations are in a different coordinate system. So it's a couple things to keep in mind that are cool, you know, in case you're interested, is that it's not the same Cartesian coordinate system that we're more used to, like XYZ, you know, polar coordinates like R and theta. It is a different coordinate system. So I mentioned about the metric and geodesic and all that. We need those types of concepts. Metric is nothing but an invariant. It kind of lets you do this coordinate system conversion, if you will. And lets us do these maths. So basically, because it's a different coordinate system and he's using 4 space-time, so there's a coordinate for time that is generally denoted by the 0th index, and then there is 1, 2, and 3. These are the spatial coordinates. So the 0th index for time, and then three spatial coordinates. So these 4 space-time. So there are 4 things, 4 dimensions, right? Time, and then 3 spatial coordinates. This type of math, it's a 4 space-time coordinate system. So it's different than what we might usually use. And so that's something to keep in mind. We do need a slightly different math to tackle this. So that's why we introduced the concepts of the metric, which lets us do this type of conversion. The geodesic is basically sort of the straight line equivalent in general relativity. I use physics. Oh, good. Hi, David and Bertie. So geodesic is sort of basically the path that a free particle would follow in general relativity. Just like, you know, in Newtonian mechanics, a free particle, if no force was acting on it, would just go in a straight line. So the straight line equivalent in general relativity is geodesic. Okay, so we also introduced the concept of the geodesic. I'm just kind of saying in short now. And then once you have this mathematics set up, you can actually see Einstein's tensor and Einstein's equation, which is basically Einstein's tensor equal to some stuff in the left, equal to 8 pi g. In fact, we will real quick say it, why not? So Einstein's equation. Ooh, another thing I forgot to say is that, by the way, because a free particle in the universe under gravity, and gravity is part of the curvature of space-time. So it's basically not considered a force in general relativity, right? So a free particle is basically the same as saying the d2x I dt2 is equal to 0. Like the, yes, Fuji. Hi, Fuji. So we actually start, to get to these equations, we actually start by saying d2x I dt2 equal to 0. But then x is going to be in other coordinate system, not our usual Cartesian coordinate system, okay? The atom bomb. The atom bomb is not very difficult, but sure. If you like the atom bomb, we will talk about nuclear physics in just a little bit here. So that might be of interest to you if you like the atomic bomb. So basically d2x I dt2 equal to 0. I thought that was so cool because obviously in Newtonian mechanics, F equals ma, you know, like that, the a is the second derivative of position, right? Acceleration is the second derivative of position. So like it's the same thing, d2x dt2 times m is equal to f, but here f is 0 if you're saying that gravity is not a force, and that's how you ultimately derive these equations. We kind of went over it. And then when we come to Einstein's equations, I'll just read it out real quick because I think it's cool. So G mu nu, capital G mu nu, this G is Einstein's tensor. Yes, Fuji. Yes, Fuji, come. Mama loves you. This big G is Einstein's tensor. I know it's confusing because, you know, just capital G is the Newtonian gravitation constant, and that's part of this equation too. But anyway, Einstein's tensor is equal to some stuff on the left is equal to 8 pi g t mu nu, where t mu nu is the energy momentum tensor. So basically Einstein's tensor, now the stuff on the left, I'll just say it, it's the Ricci tensor minus 1/2 small g mu nu Ricci scalar. So that's what is going to ultimately give us the A's back in this whole situation. Like, remember I talked about the scale factor small a and getting it in, you know, where is it in this whole thing? It actually comes into play because of the Ricci curvature and the Ricci tensor. Hi, Mekhello, sorry. Hi, Grimace, who said Mekhello, everyone. Hi, hello, Grimace. Yes, Fuji. Huh, baby? Yes, baby. Mama loves you. Fuji is being very demanding at the moment. He wants attention. Oh, good job, Fuji. He's playing with his toy he wants me to see. Good job. Let me show you guys. Good job. Oh, look at him. Oh, good job. Good job. Good job. Good job, babies. Sorry about the interruption, but I think it's very cute. Oh my goodness! Look, 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 look. Look at Fuji. Oh, Fuji! Oh, good job! Wow! Thank you so much, Fuji. Thank you so much. That's the gift he brings me all the time. Not all the time, every night. Good job. Love you, baby. Can I teach cosmology now again? Good job. You did such a good job. Okay, so so basically Einstein's tensor is equal to 8 pi g t mu nu. That's the Einstein equation, okay, for general relativity to describe the universe, pretty much. And where we get the small a back, where the scale factor comes back, is because of the Ricci curvature and the Ricci tensor, which is on the left-hand side of this. So we kind of went through all this. So we also covered the Ricci tensor, the Ricci scalar, scale factor, how it comes back into the picture through this, Einstein's tensor, and the energy momentum tensor. And guess what? That rho that I mentioned earlier, the energy density of the universe that came into the equation for the Hubble rate, that energy density comes into play because of the energy momentum tensor. The energy momentum tensor, T mu nu, which is on the right-hand side of this equation that I'm talking about right now, gives us rho as one of its components. So we kind of touched upon and went through this math a couple of lives ago. So if you want to like listen to it and if this is relevant to your work for some reason, if you're like a student in cosmology or physics or astronomy or anything like that, and you want to kind of go over it, or if you're just interested how the, how the tensor and how the general relativity math kind of works and what is the basic setup of the math. I'm not saying that we exhaustively covered all of the math, but we did set up the basic equations and basic setup of the math that you would need to set up general relativity for the universe, okay? So after all this, we come to a more qualitative topic. So I didn't want to spend every live stream talking about all of the equations and the math because I realize it can be a little confusing. And I also realize I need a whiteboard. I need to buy one. But pretty much, I also thought that there was some value to covering the math in the way we did in that particular live stream, just because it's all the basic stuff. Today, we will kind of touch upon, again, the more qualitative discussion, which is sort of a more qualitative description of the universe and its evolution. So let me remind you that pretty much when we talk about cosmology and the cosmic inventory, there's really only 5 types of things in this universe, okay? So it's not too bad. Number 1, photons. Number 2, baryons. Number 3, dark matter. Number 4, neutrinos. And number 5, dark energy. Out of these 5 things, we understand 3 things. We understand photons, baryons, and neutrinos. Baryons are basically protons and neutrons. In the discussion we had earlier to figure out how much of each thing there is, the author of this book, Scott Dodelson, that we've been referencing, pretty much lumped together baryons, which is protons and neutrons, technically, also with electrons. Electrons are not technically baryons. They're fermions or leptons in the particle family, but that's okay. We saw, shocking, that baryons were only responsible for around 5% of the energy density. Hi, Orange Kitty. How are you? So, baryons, which is basically all of the ordinary matter of the universe, accounted for only 5% of the energy density. This was pretty big news. We covered all of the different evidences that were useful in figuring this out, how they figured this out. Some of it was like there was quasars at a distance, and then there was light coming from them, and we looked at how much light was absorbed by the intervening hydrogen. We also remembered that actually most of the universe, elementally, if you're thinking what is the most abundant element in the universe, quiz question, can someone guess what is the most abundant element of the universe? You're either right or wrong. Doro, tell me. Take a guess. What is the most abundant what is the most abundant element of the universe? Take a guess. It's okay, I work online. There's always gonna be haters. No worries. I worked in corporate America. You can't hurt me. Oh, and I worked in academia. You really can't hurt me. Not light. I meant abundant element. So it has to be one of the periodic, the periodic table of elements? It has to be one of those things. So you're right that light is a cosmic ingredient. But when it comes to, that's okay. Architect, that's good. Architect, oh good. Well, that's a hard job. So, well, you will know after today. Their food is about to fall. The most abundant element, as in, okay, so the most abundant element as in of I'm talking about like matter now, ordinary matter. The most abundant element is actually hydrogen. So in the universe, in all of the universe, it was the first element that was formed. The first real like atom that was formed was hydrogen. The sun, is making helium out of hydrogen. It's the main job of the sun. So hydrogen is still very important. Yes, 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 yes. So hydrogen is very important. It's very abundant. It's pretty much the most abundant thing still. As far as the elements go, I'm not saying that it's the most abundant thing overall, because we know that baryonic matter, so all of the baryonic matter in the universe only make up like 5% of the overall energy density of the universe. So I understand it can be a little bit of a confusing thing when I suddenly asked about the most abundant element, because you're right, we're considering all of the types of ingredients now. So again, the cosmic inventory is basically photons or light, baryons, which is mainly neutrons, protons, and electrons. For this discussion, generally speaking, electrons are not baryons. Dark matter, which we'll look into, it's something we don't really understand exactly what it is, but it contributes to the total matter density of the universe. And then lastly, wait, did I say all of them? Photons, baryons, dark matter, neutrinos, and dark energy. We understand photons, we understand baryons, and we understand neutrinos for the most part. Neutrinos were mysterious to us a while ago. They're a more recent thing. They're a more recent thing, but these three we understand, we've tested, we've measured. These things are good. We kind of get it. The stuff we don't get, but the stuff that seems to dominate the universe's makeup, as in what the universe is mainly made of, is dark matter and dark energy. We don't understand what these things are. Basically, we found that some other matter was contributing to the total matter density of the universe, which wasn't baryonic. In other words, which was not made up of ordinary matter, like ordinary neutrons, protons, electrons type of stuff. And that was another evidence of dark matter, basically. And we also have some other evidence of dark matter, but we saw how sort of dark matter was discovered in the cosmology point of view, cosmologically, what their importance is. We actually found that so cosmology is basically like a really large scale type of physics, right? Because something like, say, our sun, our moon, our solar system, like our own galaxy, our galactic center, these would be examples of astronomy or astrophysics. I'm not saying that the astronomy and astrophysics are limited to just these things, but basically astronomy and astrophysics is a little bit more specific. We might have a bit more of a specific object in mind or system in mind when we do astronomy or astrophysics, like probing the supermassive black hole at the center of our own galaxy, or looking at our neighboring galaxies, or looking at a source of gamma rays far, far away. Those types of things are more of an example of astronomy and astrophysics. Cosmology, on the other hand, is a more generally speaking and more broader and bigger scale look at the entire universe, and really tries to understand the evolution of the universe from the Big Bang to where it is now. So that's where these things are kind of different. And of course, so that also gives us a different type of view and insight on these various different topics and open questions, such as dark matter and dark energy. Dark energy especially, I would call it a more of a cosmology type of topic, because of course it started as the cosmological constant. It comes out very it comes out as something you absolutely need when talking about the expansion of the universe. It's basically synonymous with that, and it's something that also cosmological models have proved out. And those types of experiments that they looked at actually far away supernovae data, or supernovae data at different redshifts, to see that the universe was actually indeed expanding. And this expansion was possible when you took into account a cosmological model that includes dark energy. But we still don't know quite what it is. So that's definitely a cosmological question. Dark matter, on the other hand, can be approached from various directions. It can be approached in an astronomy kind of way, an astrophysics kind of way, a particle physics kind of way. But we also saw how it was approached from a cosmology kind of way. So that's where the discussion on dark matter was important, because it motivated certain cosmological efforts for us. So now that we have summarized, Fuji, no Fuji, come. No, baby. So now that we have kind of summarized what we talked about so far in the previous lives in terms of the universe, its expansion, the smooth universe, and most importantly, the cosmic inventory, we will get started with our next topic. Which is going to be a little bit more in depth on the Big Bang nucleosynthesis. Hi, Fuji Suji. They're fighting now. So thank you everybody for all your patience. If you're watching this as a video upload later on, please do leave us a comment. I'm gonna have to get up in the previous ones. Feels like a back in college. While cool, lots of info, good problem to have though. Yeah, I have lots of videos now. I'm basically creating a big backlog of all these videos that kind of take you through these topics. So especially if you found the modern physics of the 20th century stuff to be more interesting, or you have some interest in that, like the Einstein discoveries back in the 1900s, especially for relativity and quantum mechanics, then I have a lot of videos on that. Especially in the month of like October and November, I believe that was when I was covering it, like every time I was going live pretty much. So I might have to go back and rename some of these lives. Sometimes they're just called soothing live or relaxing live, because I'm not like sure exactly what I'll be doing in the live, right? I know it'll be something with the kitty cats, but generally speaking, we were covering those topics. But I might have to go through and rename some of them. But nowadays, pretty much from the end of November-ish to now, timeline, we have been covering astrophysics, astronomy, and cosmology pretty much back to back to back. So far, whatever I said is sort of a summary of what we looked at. The cosmic inventory is a very important topic. Again, the universe has photons, baryons, neutrinos, dark matter, and dark energy. We will now look at a little bit more in depth about this, and we will now talk about the Big Bang nucleosynthesis. So we have mentioned, so by the way, the book that I've been referencing in these discussions is called Modern Cosmology by Scott Dodelson. This is a staple book of cosmology. And so basically, when I talk about these topics, I use both sometimes a sort of popular science level of educational material, and sometimes like actual real textbooks that are taught from in the, in university, basically. So this book, for example, is a university textbook. It would be required, reading and required exercises for people who are going to be majoring in physics, with a concentration in cosmology, probably at the grad school level, okay? So this is, it might be sort of an advanced class in undergraduate physics, but this is sort of more of a grad program level kind of book. But we're not necessarily covering every equation and everything in super duper detail. And so I'm thinking that this should be mostly digestible, and I also repeat myself a lot, and I'm happy to explain things again and again. Because I do realize that it's not exactly like, it's not like a, it's not super light reading exactly, but I'm hopefully still using it as a reference so that we can have these discussions and I can still cover the topics, because they're very important topics, and I don't necessarily want to pull the information out of like sort of iffy sources. So just know that for the cosmology topics and also for the astronomy and astrophysics topics, we're actually using university textbooks as the reference material so that you know that you're getting the correct information, or at least the information that we have the most faith in. For example, I covered dark matter candidates from an astrophysics point of view, and we looked at it from that introduction, Foundations of Astrophysics book written by professors at Ohio State that I used to actually work with. So they gave it to me for free, thank God, because these books can be kind of expensive. So, you know, these books, luckily, because I was in academia, I have these books. So let me just show you real quick. This is the Foundations of Astrophysics book that we have also referenced in the past, written by Barbara Ryden and Bradley M. Peterson. Hi, Anthony. We've also referenced this, and we covered actually dark matter candidates from this. But what I'm trying to say is we have been covering more textbook references, but we will also cover, I have to go to the library and get some more books actually for the more popular sciencey approach. We will do that as well. So just bear with me. I'm trying to kind of go through these topics, dark matter, dark energy topics, as well as these cosmological topics, you know, at these different live sessions. I think you'll learn something new every live stream. So I do appreciate you coming to these lives and kind of seeing the topic, even if we have covered it already, you might just hear it again, and hopefully it helps to kind of go through it. So that's what we're going to be doing here. And the other thing why I have also been covering this is because, you know, if you're in the US, your taxpayer dollars are used to do all of the current research in physics, and the two biggest open questions in physics are, of course, dark matter and dark energy and dark matter, depending on how you want to count, because dark energy is more dominant in the universe. Maybe we should count that first, dark energy, and then dark matter. And these are very large collaborative efforts and whatnot, and they're also kind of complicated. So I find that it would be good to educate the masses on these topics, because then you kind of know what's going on, and you yourself could also contribute to these topics as well. We might need, you know, help from people who, if they're, say, trying to decide the major that they want to pursue in college or something like that, or the research topic that they want to pursue, they might also benefit from these types of discussions. So here we are. So Big Bang nucleosynthesis. So I mentioned at one point that the universe has evolved a lot. At this current moment, the universe is almost 14 billion years old. Now, we have some data of the universe at various ages of the universe. Sometimes we call these epochs. The epoch of the universe where it was more radiation dominated, or the epoch of the universe where it became or started to become more matter dominated, things like that. But basically, the universe has gone through a lot of evolution. And how the universe got started is called, it's given this term called Big Bang. There wasn't really a bang, and it wasn't really big, but the name has stuck. But soon after, okay, Dora Dora, all right, have a nice sleep, and appreciate you being in the live. So the Big Bang is what we call the beginning of the universe. And pretty much, I mentioned earlier how the early universe, it was a very different environment. So just kind of try to imagine it. There were no us, you and me, we come much later. No cats, no trees, no earth, no sun. Indeed, there were no stars, right? Definitely not something like the sun. Like the earliest stars would form later, the first stars, you know, the first, sometimes people call them the first generation of stars, because stars also kind of die and they spew the matter everywhere. And that's how we get elements. Elements are formed in stars, most of them. Really the element that the universe made on its own is hydrogen. Pretty much after that, there might have been a little bit of helium. We will see actually in this topic how much helium or how that ended up being. But pretty much most of the elements beyond helium are made in stars. But in the beginning of the universe, there were no stars. Stars will come later. Galaxies, structure, formation, all of this comes later. In the very, very beginning is the Big Bang. And the Big Bang actually made some stuff. So the Big Bang was not like a useless thing that did not make anything. It did make something. After that, most of the richness that we see today in the universe, you and I, elements, heavier elements, more elements, these are all made in stars. But what did the Big Bang make? Did the Big Bang make anything? Hopefully it did. So that's what we'll read about right now. So in short, the Big Bang made photons, electrons, positrons, neutrinos, baryons. And as far as elements go, really what we pretty much got back then was mostly just hydrogen and very little amounts of helium, because just forming an atom itself was pretty tough until things cooled down more. So we will launch into this now. As the temperature of the universe cools to 1 MeV, the cosmic plasma consists of, and we will see the list now, pretty much if the temperature was over an MeV, you could not really make, everything was in this hot and dense state. It's called the radiation dominated universe, because pretty much at that point you couldn't even tell apart these things. So it's really when there's more cooling happening, we can kind of start to give credit to, okay, these were the things that were being made. So number one thing that was made, relativistic particles in equilibrium, photons, electrons, and positrons. Basically, photons, electrons, and positrons were all kind of in this jumbled state together. These are kept in close contact with each other by electromagnetic interactions, such as basically the electron and positron can react together to give you gamma rays. There's a famous interaction. Let me show it to you. Let me write it down and show it to you. So basically, at this point, photons, electrons, and positrons. Positron is the antiparticle of the electron. Nothing too strange. Oh yeah, pretty much. This is the interaction right here on the bottom here. See, electron and positron bumping into each other, making gamma rays, or gamma rays making electrons and positrons. This sort of thing was happening, say, nonstop. Pretty much in equilibrium, this was happening. Besides a small difference due to fermion-boson statistics, these all have the same abundances. So pretty much in the beginning, as the temperatures cooled to around an MeV, the cosmic plasma had relativistic particles in the form of photons, electrons, and positrons. These were pretty much in equilibrium. They were constantly turning into each other, doing a whole dance, and it's relativistic, super duper hot still, super excited still, and whatnot. Okay. And you will see that electrons and positrons kind of have the opposite charge to each other, right? And a photon does not have charge. So basically, electrons and positrons kind of interacting to make gamma rays kind of conserves that charge. And then gamma rays making electrons and positrons also conserve that charge. And so there might be, now, photons are technically bosons, and electrons and positrons are technically fermions. And these two different types of things, fermions versus bosons, are given by different types of statistics. So that's why they mention here fermion/boson statistics can be a little different, but pretty much at this point, things are so hot still, and things are such in a sort of still a very confused state of everything becoming everything. And so it didn't matter too much. They pretty much we had photons, positrons, and electrons in the same-ish abundances at that time when the universe is cooling down to around 1 MeV, okay? Next in the list is decoupled relativistic particles. So what's the decoupled relativistic particle? This is neutrinos. We talked about neutrinos, how they're still an ingredient of the cosmic inventory. And these were formed even back then. So there are a bunch of other types of reactions and interactions in particle physics and in nuclear physics even now that make neutrinos. The sun makes neutrinos. So nothing strange there. But even back in the Big Bang and following the Big Bang, we had neutrinos. So these relativistic particles actually decoupled at temperatures a little above 1 MeV, the rate for processes such as new electron going into new electron. So like electrons and neutrinos kind of interacting with each other, which keep neutrinos coupled to the rest of the plasma, drops beneath the expansion rate. Neutrinos therefore share the same temperature as the other relativistic particles. So let me give you this particular interaction as well. So this is basically neutrinos and electrons doing a dance together. It just looks like that. And this type of interaction, the process of neutrinos interacting with electrons, and again, this is it's still very hot at this point. We're still sort of in a plasma state of the universe at this point. It's called cosmic plasma, right? Like it's still very beginning stages. We're counting this under Big Bang nucleosynthesis, right? So this is still sort of the Big Bang-y type of environment. Like we've had the Big Bang, whatever that is, and we've started the universe. We're still sort of in a plasma state. So at this point, because, you know, everything is hot, dense universe, the neutrinos were coupled to the rest of the plasma, drops beneath or at temperatures a little above 1 MeV, the rate for processes such as this one that I mentioned, which keeps neutrinos coupled to the rest of the plasma, drops beneath the expansion rate. So if the rate of doing this process drops beneath the expansion rate, then the neutrinos will decouple. Neutrinos therefore share the same temperature as the other relativistic particles and hence are roughly as abundant, but they do not couple to them. So if the rate of doing this type of thing, if it was happening at the same or lesser rate as the expansion, then the neutrinos would also kind of stay coupled with the, you know, the electrons, and the electrons, positrons, gamma rays, those we know are in equilibrium of a mess of their own. But actually the neutrinos kind of decouple because the expansion rate is above this, the rate of this happening. Isn't that so interesting? At temperatures a little above 1 MeV, the rate for processes such as the nu E, which the electron neutrino, the neutrino and electron interaction, which keep neutrinos coupled to the rest of the plasma, because the plasma is mainly electrons, positrons, and photons, remember, that are all kind of freaking, you know, dancing together. So this would have kept the neutrinos coupled to the rest of the plasma, but it drops, the rate of this happening drops beneath the expansion rate, the expansion of the universe, that rate. Neutrinos therefore share the same temperature as the other relativistic particles and hence are roughly as abundant, but they do not couple to them. So they're decoupled from the plasma. And next, the third type of thing happening in the plasma or in this era of the universe, which is basically shortly after the Big Bang, is we get non-relativistic particles or baryons. If there had been no asymmetry in the initial number of baryons and antibaryons, they then both would be completely depleted by 1 MeV. However, such an asymmetry did exist initially, and this ratio remains constant throughout the expansion. So basically the baryon-antibaryon ratio or numbers were not the same. By the time the temperature is of order 1 MeV, all antibaryons have annihilated away. And so we get, there's a little equation now, the number of baryons, which is given as number of baryons over number of gamma rays, is equal to 5.5 times 10 to the negative 10. And then we have the total baryon density of the universe, h squared over 0.02. So thus there are many fewer baryons than relativistic particles when the temperature is around 1 MeV. So 1 MeV is still a very hot temperature to successfully make, for example, atoms. Baryons are mainly protons and neutrons, right? So when you start to make atoms and things like that, then you would probably have more baryons. At this stage, this is all still very radiation dominated. Remember, we said the universe in the beginning was radiation dominated. This is sort of that sort of moment still. Our task in this section will be to determine how the baryons end up. Were the system to remain in equilibrium throughout, the final state would be dictated solely by energetics, and all baryons would relax to the nuclear state with the lowest energy per baryon, iron. So iron has the lowest energy per baryon, and remember, a baryon is protons and neutrons. So per baryon meaning per either proton or neutron. However, nuclear reactions, which scale as the second or higher power of the density, are too slow to keep the system in equilibrium as the temperature drops. So in principle, we need to solve the equivalent of a Boltzmann equation that we have skipped for our discussion today, but there is such an equation for all nuclei that is a set of coupled differential equations. In practice, at least for a qualitative understanding of the result, we can make use of two simplifications that obviate the need to solve the full set of differential equations. Thank goodness, because we're not going to go into the Boltzmann equations too much. We kind of skipped over the Boltzmann equations for the different types of materials in the plasma for this particular discussion. I just wanted to jump directly into the Big Bang nucleosynthesis. So again, to recap, the Big Bang made some stuff too. It's not so, because right now the part of the universe, the evolution of the universe where we're talking, does not have any stars. There's no you and me, there's no cats, no trees, no us, no earth, no sun, no stars, right? Like not even the early first stars or the first generation of stars, which would, die and make the next generation of stars. We don't have any of that yet. We are at a temperature of around 1 MeV. So that's like 10 to the 6 of an EV. And we'll get into sort of some of the energies of nuclei and atoms going forward, and you will see that 1 MeV is still kind of high, in terms of making atoms and things like that. So we are pretty much, this is what we call radiation-dominated epoch of the universe, and relativistic particles in equilibrium is like the king of the jungle, and the king of the jungle here is basically photons, electrons, and positrons all sort of in an equilibrium dance together. Electrons and positrons are constantly, bumping into each other and making gamma rays or photons. Photons are constantly bumping into each other and making electrons and positrons and being very high energy, dramatic type of environment. So that's the first type of thing. Relativistic particles in equilibrium, photons, electrons, positrons. Next type of thing that the Big Bang made is decoupled relativistic particles or neutrinos. These neutrinos would have stayed coupled to electrons or the plasma that we just stated above, but turns out that the rate at which they were being made was sort of below the expansion rate, and so neutrinos became decoupled. They have about the same abundance and same temperature as the other relativistic particles, but they are indeed relativistic. They get decoupled and they're sort of free. The neutrinos are sort of like, I'm gonna leave the party, guys, bye-bye type of thing. And then thirdly, we also had little bits of non-relativistic particles or baryons. And turns out that there were baryons and antibaryons. We kind of lost the antibaryons because of an asymmetry in how they were made. And in general, though, we made much fewer baryons than we made relativistic particles in those types of environments of the Big Bang. So shortly after the Big Bang, if you ask any of like the element people, like the people who care about nuclear physics and what kinds of elements were we making, pretty much we made, like shortly after the Big Bang, we made, if we started to make atoms, it was mainly just hydrogen and maybe very small amounts of helium. We did not make anything beyond that. So like all of the periodic table of elements, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, and above were made in stars. Okay, so pretty much the Big Bang made these relativistic photons, electrons, positrons, neutrinos, relativistic things like that, becoming very, especially the photons, protons, and electrons, or sorry, photons, positrons, and electrons, not protons. Protons are a baryon. Photons, as in light, electrons and positrons, constantly being like interacting with each other, relativistic plasma like, that was made in the Big Bang. That's what was the main thing in the universe at that time. Some neutrinos and then little bits of baryons. And in terms of atoms, I would say mainly hydrogen and very, very small amount of helium. Our sun is making helium even now, you know. So the main thing that the sun does is make helium out of hydrogen. So making helium is no joke. That's how we're all alive. We're getting power, sunlight, energy, heat, all of that from the sun, because its main job is to make helium from hydrogen. So making elements is the job of stars. It happens in stars. Depending on the type of star, you can get different types of elements, especially up to iron is very common in a lot of different stars. Also depends on the age of the star and things like that. But right now we're talking about Big Bang nucleosynthesis. There's no stars yet in the universe, okay? Okay, so now we will get a little bit of a lightning introduction to nuclear physics. So just like all of chemistry is like how electrons interact, all the electron exchanges between different atoms make molecules and you know, make up they can make complicated compounds. We are made of these molecules and compounds and things like that. That's like all chemistry. So that all of that happens with the exchange of electrons between atoms, making molecules, compounds, stuff like that. There's a full year of organic chemistry, for example, that students of chemistry and biochemistry have to take that have to do with all of that. Here, we will be talking about nuclear physics. This is mainly interactions that have to do with the nuclei. So it's not so much important about the electron of each of these atoms that we will consider, but more about the nucleus. It's almost like if you took two nuclei and fused them, what happens? Or if you took many of the, you know, what kind of interactions nuclei like to do is what we'll consider under nuclear physics, not so much about the electrons. Partly because at this point still, really you're considering, like when the temperature of things is around 1 MeV, you're not actually considering things to be atoms yet. Like it may happen, but it's rare because atoms actually take less energy. Atoms need to be less excited than that. To say that something is an atomic state, you have to have less energy and more stability than that. When things are at this hot, dense state as which the universe is right now in the Big Bang nucleosynthesis type of environment, this type of environment, basically you can treat the nuclei of various what would be atoms later as simply nuclei. You don't have to consider them so much as, you don't consider them at all as atoms yet. So nuclear physics, a single proton is a hydrogen nucleus. So even though we just said that we're not really making atoms too much yet, but we understand, you know, people think of a single nucleus as a hydrogen nucleus, right? If that nucleus were to also have an electron, that would make up the full hydrogen atom. But pretty much in the context of nuclear physics, we will, because remember, even in the periodic table, the way the periodic table advances is actually by atomic number, right? An atomic number is given by the proton number. So how many protons an element has is actually what determines what type of element it is, right? So hydrogen's proton number is 1, helium's proton number is 2, lithium's proton number is 3. So it's really the number of protons is gonna be very important here. And also the number of neutrons we will see will be important as well. Together, protons and neutrons are called baryons. And nuclear physics is more to do with this type of thing. It has more to do with proton number, neutron number, nuclei, what's going on in the nuclei, how many nuclei of something you have. This is more nuclear physics. Okay, we don't have full-on atoms in a stable state yet because the universe is at this point too hot. So a single proton is a hydrogen nucleus referred to as 1H or simply P, just small p. A proton and a neutron make up deuterium. So that's an isotope of hydrogen. When we say hydrogen atom or hydrogen nucleus, we just mean one proton. If you had one proton and with it another neutron, if you had, in addition to a proton, a neutron, you would make deuterium, which is a type of hydrogen isotope, or 2H, or D. Sometimes we just say D, or deuterium. One proton and two neutrons make tritium, or 3H, or T. So tritium, some people might say tritium, tritium, we'll just say tritium. So once again, a single proton is a hydrogen nucleus referred to as 1H, or simply a small p. A proton and a neutron make up deuterium, or 2H, or one, just D, just call it D. One proton and two neutrons make tritium, or 3H, or T. T for tritium. Nuclei with two protons. So now so that was hydrogen and its isotopes. Okay. So back when things were super hot and dense, we might have had some hydrogen and deuterium nuclei. They would still be sort of in the nuclei form. They would probably not be in atomic form. But basically we could say, yeah, there was hydrogen and deuterium nuclei back then. Now we come to helium, what it takes to make helium, right? And we're talking about the helium nucleus. So all of this is going to be at the nuclear physics level, not the chemistry level. Nuclei with two protons are helium. So two protons together, two protons, that's helium. These can have one neutron, this would be 3He, or two neutrons, which would be 4He. Thus, unique elements have a fixed number of protons. So that's what I was saying. In the periodic table, which is common to use in chemistry, when we advance in the periodic table, hydrogen, helium, lithium, we're actually advancing the atomic number, which is given by the number of protons. And basically, if we have more neutrons and therefore a different number of total baryons in the nucleus, that actually gives us isotopes, isotopes, isotopes of a given element, having differing number of neutrons. So hydrogen is hydrogen because it has one proton. If it has two protons, we would call it helium. So a hydrogen nucleus is a hydrogen nucleus if it has one proton. It can be an isotope of hydrogen if there was a neutron along with the proton, then we would call it deuterium. If there were two neutrons along with the proton, we would call it tritium. But as soon as there are two protons in the nucleus, we call it helium. We don't call it hydrogen anymore, okay? So the type of element is given by its number of protons, whereas if you have a different number of neutrons in the nucleus, you might just be having an isotope of the same element. So unique elements have a fixed number of protons. Isotopes of a given element have differing numbers of neutrons. The total number of neutrons and protons in the nucleus, the atomic number, is a the total number of neutrons and protons in the nucleus, the atomic number, is a superscript before the name of the element. So maybe I'm wrong, but I think in chemistry, the proton number is equal to the atomic number. Am I wrong in saying that? Here in this book, they're saying it's just a definition, so it doesn't matter. But in this definition, he's saying the total number of neutrons and protons in the nucleus is the atomic number. Okay, whatever. I think we still agree in the sense that in the periodic table too, as you advance in the periodic table to become a heavier and heavier element, it goes by the proton number. It's the number of protons in the nucleus that makes it a new element, pretty much, which is the same here. The total mass of a nucleus with Z protons and A minus Z neutrons, where A is going to be the total number of protons and neutrons, differs slightly from the mass of the individual protons and neutrons alone. This difference is called the binding energy. So this is really interesting stuff. So the binding energy, or B, is basically Z times MP, where M is the mass of the protons, plus A minus Z Mn, where that's the mass of the neutron, minus M, where M is the mass of the nucleus. For example, the mass of deuterium is 1875.62 MeV, while the sum of the neutron and proton masses is 1877.84 MeV. So remember, deuterium is an isotope of hydrogen which has one proton and one neutron in the nucleus. So, but if you take the mass of deuterium, or the deuterium nucleus basically, is 1875.62 MeV, while the sum of the neutron and proton masses are 1877.84 MeV. So here in this case, the binding energy of deuterium is 2.22 MeV. That's a pretty number, 2.22. Nuclear binding energies are typically in the MeV range, which explains why Big Bang nucleosynthesis occurs at temperatures a bit less than 1 MeV, even though nuclear masses are in the GeV range. Neutrons and protons can interconvert via weak interactions. So like a proton and a neutrino can give you a neutron and a positron, or a proton and an electron can give you a neutron and a neutrino. A neutron can become a proton and an electron and a neutrino. All these types of nuclear interactions can happen. They actually happen pretty commonly, where all the reactions can proceed in either direction. So they're always with double arrows. So like a proton and a neutrino giving you a neutron and an electron, or a positron actually, can go both ways. This can happen and this can happen. Same thing with the proton and an electron giving you neutron and neutrino. Both ways can happen. Same thing with the neutron going from a neutron to a proton plus an electron plus an neutrino. Both ways can happen. The proton and the electron and the neutrino can also go this way to give you a neutron. So all of these are examples of nuclear reactions, and they can all happen in both directions. The light elements are built up via electromagnetic interactions. For example, deuterium forms from proton plus neutron giving deuterium plus gamma rays. And deuterium plus deuterium gives us neutron plus 3He, so the isotope of helium. After which 3He plus deuterium gives us proton plus 4He, producing 4He, which is the helium isotope with the 2 protons and 2 neutrons, which is going to be important. So all of this was like a lightning round introduction to nuclear physics. Hopefully that all kind of makes sense. This binding energy thing that we just talked about, which is that when you have a neutron and a proton, add the masses together, you get 1877.84 MeVs. But when you get the mass of deuterium, which is a hydrogen isotope having a proton in the nucleus as well as a neutron, then that mass is only 1875 MeV-ish. So the difference is 2.22 MeV, because basically when you combine these particles to make a nucleus, it's basically this state of better stability that you get. It's almost like this, like we're good, like we're stable into this nucleus, and now we're good type of thing you get. And this binding energy will be very important coming up. You'll see that. Just the nuclear binding energies are typically in the MeV range. And so it also makes sense that we're talking still all nuclear stuff, because these types of interactions happen at the MeV energy scale, which is the energy scale supported by the shortly after Big Bang time period. Things were cooled, but not so cool. And at this not so cool phase, what you would do is nuclear physics. You still don't really consider things as atoms. Like the electrons are not necessarily attached yet to the nuclei of these things. So they're not really, you don't really get neutral hydrogen atoms in this type of environment yet. But we can do a lot of this stuff right now that we're talking about, which is really the combination of things to make the nuclei. And even making nuclei is important because we ended up with hydrogen nuclei, isotopes of hydrogen nuclei, and some helium nuclei as well. And this type of being able to make the nuclei is also important for eventual evolution to make even more things, because basically if you can make these types of nuclei, then in other types of environments going forward, depending on energies, we will make other types of elements. And that's how we started to make the elements later on in stars especially. But this nuclear reaction that we just talked about, the combination of two of hydrogens to make helium, is something that is happening right now in the sun. So that's how we get all our energy from, actually. So we'll keep reading about this. Actually, you'll see that there's a special significance to helium, which will be very important in its stability. So the first simplification is that essentially no elements heavier than helium are produced at appreciable levels. An exception to this is lithium. So we're still talking Big Bang nucleosynthesis. We talked about how shortly after the Big Bang, we made a bunch of relativistic plasma type of stuff. Hi, Molly. How are you? Yay, hi. Yes, missed you. How are you doing? Any fights in school? I hope everything is non-violent for the most part now. Yes, missed you very, very much. I'll just summarize for you. So we just talked about Big Bang nucleosynthesis. Hi, Omar. Hi, Omar. Sakar. Thank you for the emojis. Hi. So shortly after the Big Bang, which is how the universe got started, we had basically relativistic particles in equilibrium, like photons, electrons, and positrons, all kind of interacting with each other and being a hot mess, quite literally. We also had some decoupled relativistic neutrinos who were pretty much interacting with these same things, but they got a little bit away, as in they had a little bit of a breakup with the electrons and this plasma because of the expansion of the universe, and they got away. And then lastly, we also talked about having non-relativistic baryons, and within that we started talking about nuclear physics and how basically these baryons are basically protons and neutrons, and depending on temperatures and depending on the environment, if you made if you had just a single proton, we would call that the hydrogen nucleus. If we had a proton and a neutron kind of together, we would call it the isotope of hydrogen deuterium. If you had a proton and a couple of neutrons, you would call it tritium, or another isotope of hydrogen. And in those early types of environments, we actually did have hydrogen nuclei and helium nuclei, and that's pretty much what the Big Bang made. So if anyone asks a quiz question of which elements, these are not really elements yet because you don't really get the neutral atom form of these yet in the Big Bang or shortly after the Big Bang. But if anybody asks the quiz question, which nuclei were made, really technically nuclei, or even elements if they misspeak, then the answer would be mostly hydrogen. We mostly had hydrogen nuclei in terms of the baryons, and some helium nuclei is and some helium nuclei, a little bit of helium nuclei is all we made in the Big Bang. We did not make elements above that. And indeed, in astronomy, we call all of the elements above helium metals. Is there any new people? I think so. I think a lot of the people coming and going have been new. Doro was here for a while, but then I think he had to leave. I'm not sure if he's still there. And then some of our regular people are still not here. So you might still be early, Molly. I know. It's been more quiet and lonely today. But I appreciate everybody who's here. Thank you so much. Thank you, everybody. So yeah, quiz question. Which nuclei were made in the Big Bang or shortly after the beginning of the universe? Answer is hydrogen and a little bit of helium. Pretty much anything above that, maybe very tiny amounts of lithium, but um, it's one. Yeah, it's 1:42 in the morning, and that's early still for this live because we've been going so late. Sometimes we do the live for forever. And I don't know why. Like, usually around now, there's like 25 people sometimes, but tonight it's been quiet. Anyway, so the nice thing about the Big Bang, I don't know if it's really that nice, but in general, a simplifying fact about the Big Bang is that essentially no elements heavier than helium were produced at appreciable levels. Pretty much, we only had the only nuclei that need to be really traced from the Big Bang are hydrogen and helium, maybe very small amounts of lithium, but mainly, yeah, hydrogen and helium, with the isotopes being mainly deuterium, tritium, and helium. So hydrogen, helium, their isotopes, deuterium, tritium, and helium-3. The second simplification is that even in the context of this reduced set of elements, the physics splits up neatly into two parts, since above temperature of around zero point 0.1 MeV, no light nuclei form. Only free protons and neutrons exist. So if the temperature is above around 0.1 MeV, then no light nuclei form. We're talking only light nuclei right now anyway. It's not like we'll make an iron nuclei in this environment. You know, that's only possible to be made in a star. So right now we're only talking just light nuclei. So the second simplification is that even in the context of this reduced set of elements, the physics splits up neatly into two parts, since above a temperature of around 0.1 MeV, no light nuclei form, only free protons and neutrons exist. So the protons and neutrons are just kind of free at this point. Therefore, we first solve for the neutron over proton ratio, and then use this abundance as input for the synthesis of helium and isotopes such as deuterium. So these types of things kind of help us do the math of that time, pretty much. By just looking at energies and temperatures, it's kind of simple in that sense. Now we will talk about binding energy per nucleon. We will look at that, but first let's keep going. Both of these simplifications, no heavy elements at all, and only N over P above 0.01 MeV, rely on the physical fact that at high temperatures comparable to nuclear binding energies, anytime a nucleus is produced in a reaction, it is destroyed by a high energy photon. So remember how I was saying that the early universe was very dominated by radiation, and these photons were king of the jungle. They were constantly disturbing everyone, and they were constantly hitting everything. It was so hot, so dense, the photons were everywhere, and even if you were, say, trying to become a nucleus, trying to do something, you would just get hit by a photon and get all this extra energy, and you couldn't become a stable nucleus. So this fact is reflected in the fundamental equilibrium equation. Let's see what that is. Oh yeah, something about, that's okay, whatever, it's a detail. Becomes, so the fundamental, to see how, let's consider this equation applied to deuterium production. So that's going to be neutron plus proton giving you deuterium plus gamma rays. Hi, Omar. Oh, okay, thanks. Oh, hi, Molly love. Wait, Molly love, are you saying you're tired? I didn't see that. Did you leave your live on last night? No, I made noodles last night. Remember, were you not there, Peter? I made some noodles. Molly. What's up, Molly? Thank you guys for being here. You are my only friends in life. Yes, I made shin noodles last night. Shin. I made shin. I'm sorry, 1 second. Now I'm feeling sleepy now. Not really, we'll keep going. But basically, wait, I can't, I have to get this closer. I feel like something's in my eye. Tried seeing if you come back on your live. Oh no! Yes, we've been going live every night. Oh, thank you. I only have 2 real friends. Me too. At this point in life, Molly, I also have very few real friends. But physics is my friend, and my babies, as in my kitty babies are there and physics is there. Pretty much, I also don't have too many friends. But that's okay. I have 1 or 2 friends, and right now, guess what? They're all traveling. Nobody cares about me. They're all traveling. They've already started all their like holiday vacations. They're all out of town. V and Nate. Oh, yay, V and Nate. Hello. Where are you? Where are you, V, and where are you, Nate? All good, you're here. I'm here, everyone here, the 3 of us. Yes, Peter. Yes. Peter, which country are you in? Are you said afternoon. Are you in Hawaii? They're 6 hours behind. Or wait, are you in Australia? I'm trying to figure it out. You only need a couple of good friends to share your life with. Yes, indeed. That's so true. Australia. Aussie. Okay. Perfect. Wait, don't leave, guys. Don't leave me. This live has been too painful. Please don't leave me. Can you please stay till the end, all of you guys? Because this is just too much. Look at my sweater. I wore a nice sweater. I wore these sponsored earrings. And nobody cares. Molly, what do you think of these earrings? Nobody said anything. My parents told me I was German. What? What do you mean, like today? Did you just find out that you are German? I love earrings. Thank you. The earrings are the sponsor of this live. So I'm glad you like them. They're from, this is the receipt. They're from Spot Mart. The product is gold earrings for women, chunky gold-plated earrings, statement earrings. Thank you, Spot Mart. I'm trying. You have very beautiful eyes. Thank you, Omar. I love your earrings. Thank you. Thank you so much, Molly. Thank you. Thank you, Peter. Thank you, Omar. You guys are making my whole night. Thank you so much. Thank you, thank you, thank you. Okay, thank you. Let me just finish this part, and then we can maybe just chat. Maybe I'll make tea. Will you hang around? Will you hang out while I make tea? I'm over it. I'm over it. So actually, let me show you one thing. So I do have to keep the discussion complete, you know, so that if people see this later on as a video, they can, you know, get a consistent picture. So look at this. This is the plot of the this is the plot of the nuclear. Okay, now that you've seen it, this is binding energy per nucleon, where a nucleon is either a neutron or a proton within an atom. So see how there's a peak there? That peak is basically helium-4. So the isotope of helium, which is helium-4, basically gets a peak. It's a very nice, stable state. And this plot that I just showed you is basically on the y-axis, it's energy over mass number, where mass number is basically protons plus neutrons. And then on the x-axis is just the mass number. Oh no, it's okay. I'll read the caption. That might help. So, binding energy of nuclei as a function of mass number. Iron has the highest binding energy. So if you guys were ever wondering what nucleus is really super stable, amazing, once you make that nucleus, nuclei are really happy. They don't want to change much after that. It's basically iron. Iron's nucleus is a very stable nucleus. In other words, it has a very high binding energy. But among the light elements, because remember, at this point in the universe that we have been talking about, which is shortly after the Big Bang, we really cannot make anything beyond helium much. There might have been trace amounts of lithium, but I really want to drive home the point that in the very early universe, in the Big Bang nucleosynthesis type of picture, we basically just have hydrogen nuclei and helium nuclei. We cannot make much more than that, let alone iron, because iron is like atomic number 26, right? Hey Google, how many protons does the element iron have?
Iron has atomic number of 26.
There. So I think I was right. Atomic number is generally the same as proton number. I don't know why at some point the author here called it neutron number 2. That's generally given by mass number. Atomic number is the same as the proton number. Molly, hang tight. Hold on. Hold my hand. We're going to be okay. So atomic number is the same as the number of protons in the nucleus. And that's what advances elements through the periodic table. So hydrogen has 1 proton, atomic number 1. Helium has 2 protons, atomic number 2. Lithium has 3 protons, atomic number 3. Beryllium has 4 protons, atomic number 4. Boron has 5 protons, atomic number 5. Carbon has 6 protons, atomic number 6. And so on and so forth. Carbon, nitrogen, oxygen. Hi! Look at who has joined me. Look at who has joined me. Neon has atomic number 10. Miss Suji. Sodium has 11 protons, atomic number 11. Magnesium. Okay, I will stop now with the periodic table. It's one of my, I don't know, one of my things I can do. So, you got a new kitten? What do you mean? That's huge news. Tell us everything. Write a paragraph on your new kitten right now. So when it comes to the number of protons, also known as atomic number, that's what gives us the various different elements. The unique element is determined by that. But then the proton number and the neutron number together gives you mass number. And this sort of overall number of how many protons and how many neutrons in your nucleus can determine your binding energy. And depending on your binding energy, your nucleus is going to be more stable or less stable. And the most stable nucleus is actually the iron nucleus. So even though iron is amazing in this department, we will not talk about iron yet because it is not one of the super light elements, which is pretty much all you could make in the Big Bang nucleosynthesis type of environment. We pretty much only made hydrogen and helium and very little lithium. That's it. So the binding energy of nuclei as a function of mass number is what I showed you with that curve with the little peak, which was important, I said. Iron has the highest binding energy, but among the light elements, 4He is a crucial local maximum. Nucleosynthesis in the early universe essentially stops at 4He because of the lack of tightly bound isotopes at A equals 5 through 8. And A is mass number. In the high density environment of stars, 3 4He nuclei fuse to form 12C, which is carbon nucleus, but the low baryon number precludes this process in the early universe. So what they're saying is, you know, in a high density environment where you have a ton of 4Hes or the isotope of helium, that is 4He, you can take multiple of them and fuse them together. You need actually 3 of them. 4 times 3 is 12 to get the 12C, which is carbon nucleus. So even to make carbon, you basically need a star, right? In a highly dense environment of a star, but in a different sort of way. It's a different environment than the Big Bang's environment. Then you can make carbon, and you can make even higher elements: carbon, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. I said that right? In the right order? Yeah, whatever. 12 carbon, aluminum 3, silicon 14, phosphorus 15, sulfur 16, chlorine 17, argon 18, potassium 19, calcium 20, scandium 21. Yeah. So all those types of elements up through like iron. Iron is another big peak. Once you make iron in a star, this will actually come up when we talk about evolution within a star. Iron is very stable. Once you have made iron, the star might not want to make higher or heavier elements, or that environment might not like to make more heavier elements because you've kind of reached a stable state, and the nuclear environment kind of likes it. Once you've made iron, you just want to finish making iron and then kind of be done for a bit. To make even heavier elements, you might need more energy and a more different type of environment. We'll get into that. A different type of process, basically, which might require a different type of environment. But basically, in the this is where the different environments and different processes of making the different elements is so important in nuclear physics. But pretty much in the Big Bang nucleosynthesis, the only thing we made is hydrogen and helium, appreciably. And oh, hi, Molly. Oh, I see some of your messages went away. I got 2 cats, actually, Sneakers and Peanut. Aww. Sneakers and Peanut? Oh, very nice. So later on, we will look at making these other elements in stars up to iron and beyond. But in the Big Bang nucleosynthesis, we just had hydrogen and helium. And in fact, this helium-4, that is the isotope of helium with the 2 protons and 2 neutrons, giving you the 4 in mass number, is a very stable nucleus. So in the Snickers, okay. Oh, sorry. Snickers and Peanut. Yes. Oh, good. Among the light elements, meaning hydrogen, helium, lithium, these types of elements, helium-4 has a very critical, very important local maximum in the peak, or a peak basically, in the binding energy. So now I'll show it to you again, and it might make sense. See how there's a peak right here? That's the helium-4 nucleus. It's basically showing binding energy as a function of mass number. And because helium-4 has this important peak, it's a very important local maximum, or local maximum as in local to this plot. And if you're only making the light elements and pretty much you don't have access to a lot of helium-4s to, you know, smoosh together to make carbon, you're pretty much going to have the helium-4 isotope as the important nucleus here. I just remembered that I have a party tomorrow. Ooh, what kind of party? That's right, it's Saturday. There might be a party. Wait, I need a tissue. I'll be right back. Don't go anywhere, guys. I need a tissue. So I think I'll take a little break, actually. We talked about Big Bang nucleosynthesis and how helium-4 is super important, and it has a peak in the local binding energy, in the binding energy plot versus mass number. And that gives us a reasoning for why helium-4, first of all, there's a simplification that we pretty much did not have any heavy elements, but also why it was possible and encouraged to make helium-4 because of its stability. In fact, let me just read this part real quick. Binding energy of deuterium 2.22 MeV. The small, let me just finish this part real quick. I have a tortoiseshell cat. Her name is Melu. Nice. Thank you guys for chatting. Yay. The small baryon to photon ratio thus inhibits nuclei production until the temperature drops well beneath the nuclear binding energy. Right. So basically there were more photons and much less baryons, the small baryon to photon ratio, because the photons are constantly beating on everything, making them more energetic, not letting things stabilize enough. So pretty much you couldn't really make too many nuclei or stay stable as a nucleus because you're getting hit with photons that are energetic and your temperatures are too high. The small baryon to photon ratio thus inhibits nuclei production until the temperature drops well beneath the nuclear binding energy. At temperatures above 0.1 MeV, then virtually all baryons are in the form of neutrons and protons. Around this time, deuterium and helium are produced, but the reaction rates are by now too low to produce any heavier elements. Here we will take a short break. I need to find a tissue and I might make some tea, actually, you guys. And since some of you are chatting, maybe I'll catch up with the chats. Okay, we are covering nuclear physics and specifically Big Bang, nucleosynthesis, and we will actually, I will show you this very important plot as I am over here. I have to find a tissue as well, and I will do this. Whoops. Very nice earrings. Are they real gold? And they look better when they're on you. Thank you. Yes, I will let you know the description of the earrings in just a second. They're gold plated, I think. The sponsor of this live sent them to me. So this is the binding energy per nucleon. Sorry, yes, binding energy per nucleon plot. Take a look at that and you will see how 4He, or helium-4, is very important. There is a local peak there, and we've been talking about it. So take a look at this plot for me as I find a tissue, and maybe I'll make some tea actually because I'm kind of freezing. Sorry, bear with me. And I will also read all your chat messages now. Excuse me. Yes, I'm still around. Yeah. If you want to get a tea, 2:07 p.m. Oh, is it really 2 p.m. in Australia now, or you mean like here? Very nice earrings. Are they real gold? Thank you for asking about the earrings because they are sponsored. Okay, well, you be back. I'm going to have a tea too now. So I already had my dinner. I had some more noodles. I had some chow mein actually, and some peanut butter and honey sandwiches. So for dinner I had today chow mein and peanut butter and honey sandwiches. I'll make some tea just now. We've been covering nuclear physics. Thank you guys for joining. And the gold earrings I'm wearing, the description of them are chunky gold plated earrings, statement earrings, and they're from Spot Mart. So that's who sponsored today's live. Thank you to Spot Mart. Okay. Thank you guys for being here. Can you promise if you're a famous scientist one day soon, you will still do lives for us? Yes, of course. Yes. Indeed. Definitely. We are covering nuclear physics. Peter says it's 6 p.m. here. Oh, in Australia it's 6 p.m. Wow. Okay, I'm gonna make some tea with you guys. Yeah, it's 2:10 here. So Molly, how is school going? How is school, Molly? All right. Yay! How is school, Molly? I asked. I'm going to make a tea back soon, mates. Okay. Making tea, then chatting more. And we're covering, let me do an emoji for that. We are covering nuclear physics. They need to make more emojis. for physics. Yeah. So yeah, we've been covering nuclear physics. We've been covering specifically the environment of the Big Bang in the early universe and what types of things dominated the universe at that time, what was in the relativistic plasma, photons, electrons, positrons, neutrinos, and small amounts of baryons, which is basically protons and neutrons. And depending on the temperature, they formed certain nuclei that pretty much dominated at that time. And these were pretty much just hydrogen and helium nuclei for the most part, and trace amounts of lithium. And the lithium ones are not worth mentioning too much at this point. We will just note that there were trace amounts of lithium. Mainly it was the hydrogen nuclei. We say nuclei because really at this point we don't have neutral atoms yet, you know, with the electron being near the nucleus and all that stuff. It's just mainly the nuclei and how the nuclei are forming with or without, of course, the neutrons. If you had just the proton, one proton only, 1p, then you would have the hydrogen nucleus. If you had a neutron along with it, you would have deuterium. If you had two neutrons along with it, you would have the tritium. And then if you had two protons together, you would get the helium nucleus. And depending on, again, neutrons or not, you could get the helium-4 nucleus. So we're pretty much we're talking about hydrogen and helium nuclei at this point. Suji, let's not do that. And we even see a local maximum for the helium-4 binding energy, giving us a stable nucleus for helium-4 in that particular environment. So what basically we were able to make nuclear physics like back during the Big Bang nucleosynthesis is going to be important, because that's what we expect to get during those early universe times. And later on, we will make the other elements, the heavier elements in the stars. But it's good to understand sort of the makeup of the universe back then, because then that's all we'll really look for, or when we find something where it's like, okay, it's consistent with what we thought, because of what we know about the energies and temperatures of that time, we don't expect to make other types of nuclei. We are not in that environment yet. We could have smooshed together more helium-4 nuclei to make carbon, which we will do in a star later on, but they simply did not have enough baryon number to accomplish that in those Big Bang nucleosynthesis periods of time. The photons were more in number, very energetic, and hitting everything and everyone, making them too excited to be able to stay stable. So that's kind of what we're talking about here. I'm making some tea. Stick around for the rest of the discussion. Thank you so much for joining the live. Okay. Hi, Suji Mama. Look at this girl. Look at this girl. Hi. Hi, Suji Mama. Hi. Hi, Molly. Did you say how your stuff was going in school? I don't think I saw that. Hi, Fuji. Hi, Suji. Ooh, and who is this over here? Baji Wawa. Baji. Who is this? Who is this? Is this a Baji baby? My thing, I know a lot about plants and nature. Plants and nature, what to eat and what not to eat. Oh, wow. Baji, Baji baby. Baji baby. Baji baby, Suji baby, Fuji baby. This one's a boy. Here, can you see it this way? 3. Did you see him give me kisses? Oh, look at this baby. This is Baji baby. This is Baji baby. Here's my earrings. This is Baji baby. Baji. 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 Cuteness attack. Oh. Hello, Baji. This is our nuclear physics break. We're taking a break with Baji. A break with Baji. Baji? Look at you. Look at Baji. An animal wild ones, mainly snakes and things. Oh, wow. Are you saying that you have snakes, Peter? An animal wild ones, mainly snakes. Oh, wow. I love this particular angle when you can just see Baji's nosy and his little face. It's like he's holding the phone. Baji! Baji! Can you see Baji's face? Can you see Baji's face? Such a Shona. You're a Shona, Baji. Shona, Baji. Shona. 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 Look at him. Look at his face. Look at his face. Oh. 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 So adorable. Thank you, Molly. Thank you, Peter. Thank you, everybody. This one is a Baji. Baji Baba. Baji Baba. I had a fox. Really? You live by yourself, you need someone, or 3 cats? 3 kitty cats. Plus I've got neighbors in the same building and everything like that. Very densely populated area here in Boston. Baji! Look at Baji's little arms. He is so, what's the word? He's so neat and clean. I love foxes. I have a fox cross cattle dog. I have a fox cross cattle dog. Her name is Amber. Really? I didn't even know that was a thing. So you go to university? Not right now. I am already done with, well, I'm always learning, but pretty much I've already finished my university programs. Baji! Oh, What is that? So look at Suji. She's being such a good girl, reading all about binding energies right here. Nuclear physics prime. Nuclear physics time with Suji. She loves it. You love it. You love it. Actually, they want a snack. So let me do that. Here you go. Here you go. My fox's name is Trix. Really? That's a good fox name, actually. That is good. Trixie the Foxy. Hi. Here, Baji, I'll give it to you in this other container. Here you go. Here you go. And my husky's name was Husker. Okay, we'll do a little tea time here. They're getting their snacky. I'm gonna get my tea going. I'm gonna get my tea going, guys. Good job. Good job, peoples. You guys fighting? What is this? Husky name was Husker. My friend's dog is on my lap like a puppy, but he's a giant. Oh. Okay, you guys can look at the nuclear physics diagram again. The plot here. That's what we're discussing. Or that's what we have been discussing. I can't get him off. Is that Husker or somebody else? No, Fuji. We just had a snack, now we will rest. Now we will rest. Alright, well, thank you so much, everybody. I'm going to make the tea, but if you are just now joining and you are looking at the nuclear physics diagram here, you can feel free to go back into the live to follow our discussion on nuclear physics here today for the Big Bang's period and Big Bang nucleosynthesis. Harlow. Oh, wow. Thank you for liking the live as well. Okay. Oh, shoot. I think my phone is dying. Might have to charge it. So Molly, are you... What's your plan for the weekend? Now I'm charging my phone. I'm a builder, built a lot of kitchen tables, venture shells. Ooh. So, I'm still waiting on my tea water here. Hopefully that is showing up. And go up to see the rest of this live in the front part. Thank you. It's good to have you. My kids can go through it one day. Oh, good. Old sewing machine. Interesting. Yes, we are covering a somewhat important topic of what was made in the Big Bang. So yeah, thank you guys for being here. I'm a little bit cold. chai latte. Yes. Yes, I worked for a number of years after my PhD. Yes, indeed. Yep. Okay, my tea is boiling. Apate. That song is stuck in my head now. Apate. Oh gosh. If you're watching this video as a video upload later on, please do leave me a comment. I think I might wrap it up tonight. We covered Big Bang, nucleosynthesis. We summarized a lot of what we've been kind of doing in cosmology for the past few lives. And we touched upon pretty much what was dominating in the universe shortly after the Big Bang and sort of the environment that we had at that time, and the relativistic photon, electron, positron, neutrino business, as well as small amounts of baryons. And we started to touch upon like what is super important in terms of these stable nuclei and binding energies, because nuclear physics is really ruled by this, you know. So understanding these things are going to be very important. Luckily, I suppose, in the early universe, we just kind of made, in the Big Bang that is, we just kind of made hydrogen and helium, and that's it. Very little amounts of lithium, and that's it. And so not too bad in terms of the things that we have to keep track from those days. So yeah. And we started to get into the conversation of the importance of binding energy, and how later on we will see that the iron nucleus is very, very stable and has a very high binding energy. So we will look at all of this again when we look at how elements are made in the different processes in the stars. But I think I'll keep this discussion short in the sense that we covered pretty much the main bulk of what was made in the Big Bang nucleosynthesis. There's a few other steps that I wanted to get into, such as with what kind of happens in the nucleus or in the universe following the Big Bang. I think we'll get into those maybe tomorrow. We'll go live again and we'll get into that. Today we had a bit of a quieter live, so I'll save that for tomorrow. And we will end with this extremely important plot right here so that you can kind of focus on that for now and see how pretty much in the Big Bang nucleosynthesis, we just kind of stopped at helium-4 in terms of the most stable nucleus. And if we had more baryons and more baryon density, we might have, been able to make carbon, but we didn't. And that is only made in the environment of the first stars later on. So at this point, we still haven't made stars in the universe. That's kind of where we are discussing today. And we will continue to continue next time on what happens next. So stay tuned with our discussion. Thank you so much for joining the live, and thank you so much for watching this video. If you're seeing this as an upload later on, do leave us a comment. Let me read your last few chat messages. Oh, wow, a farm. Goodness. No, I don't know too much about the hydroponic farms on the moon. But yeah, thank you for all your messages. Oh, perfect. Thank you. Yeah, take a screenshot of the binding energy per nucleon. Thank you, for all your messages, Peter. Thank you for sharing. The farm sounds very interesting in Australia. I actually have not visited Australia yet. I'd like to at some point going forward. I'm sure Australia is very big and pretty. But yeah, so I wanted to end with, sort of wrapping it up here, the discussion we had today. We pretty much see that as far as the elemental abundances go and the types of elements go, it was pretty boring in the Big Bang. We made hydrogen and helium, but also that would explain why there's so much more hydrogen than anything else in the universe. Remember, in the Big Bang, pretty much the only nuclei we made were hydrogen and helium. And so when we look back in time, it would make sense that we get only hydrogen and helium pretty much, and that we expect that. And when it comes up, say during our discussions of the cosmic inventory, remember, we talked about deuterium atoms. And now we understand why the nuclear physics of that environment was such that we couldn't really make other things heavier than hydrogen and helium. But these two elements are very important in the universe. Even our own sun is making helium out of hydrogen. That's the main nuclear physics work that the sun is doing, and that's how we get all of our power, energy, heat, source, all of that from the sun, and how we are alive. So we must have appreciation for this nuclear physics process and understand that this was happening even very close to the birth of the universe in the Big Bang nucleosynthesis period of time. And so that's all very interesting, and we will continue this conversation going forward next time. Thank you again so much for being here. We will continue from this particular chapter and this particular topic. We will see much more going forward, what happens next in the universe. It's kind of like a television series, but except this is the real evolution of the real universe that we live in today. So signing off for today for now. Thank you so much again for all your chat messages and for all your contributions. A little bit of a quieter live today, so hopefully many of you will see this video as an upload later on and let me know any of your comments. And I hope to see you tomorrow for Saturday's live and Sunday's live and Monday's live and Tuesday's live. So thank you. Thank you, Peter. Thank you, everybody. There's always time to learn more. Thank you. Yes, absolutely. Love it. Peter says there's always time to learn more. That's absolutely right. Much appreciated. Thank you so much, everybody. Ooh, and also I wanted to say that if any of you want to, please share the live or share my videos with any friends of yours. That would be amazing. If you think that anybody would benefit from these conversations and if they might have a similar interest, feel free to share it. Oh, wow. Campfire. Good. I love fires, actually. So yes, please do share my live and watch my videos. You can go to the channel and actually, Peter, if you're trying to catch up with all the different topics that I've been talking about, then you just have to go to my channel under the live tab and you can play pretty much all of the videos going back. You could start maybe in October or so timeline and listen to all of the videos, and that'll catch you up on all of the physics and other discussion sort of from the 20th century stuff that I was talking about, Einstein's work. All of that is covered in all of those earlier videos. So if you'd like to catch up on that, feel free, and thank you so much. Yes. Yes, Peter. So once you watch those videos, leave me a comment too so I can read about what you thought. And sometimes it kind of helps me to remember what I talked about in my own videos from a while ago. So if you go back to the October timeline and if you leave me a comment on that video, that would be actually most helpful. October and November. So yes, then you'll know more about what we're talking about. Exactly. That would actually be very, very helpful for the discussions going forward. And also for me to remember what I talked about in October. And I might go back and rename some of the titles of those videos, actually. So it would be very helpful if you view those videos and or, even if you're just listening to them or something, and leave me a comment. Thank you. Okay, I can do. Thank you so much, Peter. Thank you. That's very helpful. Thank you. Okay, I can do now. Oh, good. Thank you, thank you. Bye. Actually, I'm going to make my tea and leave this on for now. Oh, hi, Kayla. How are you, Kayla? Have you been, did you just come in? Did you see the live tonight? If you want, Kayla, you can go back in the live, like just kind of go back into it, and then you should be able to see the full discussion of today. We covered Big Bang, nucleosynthesis. Just got off work. I didn't see earlier. Okay, no problem. Are you able to go back into the live and see it? Okay, I'll save it. Okay. And the live should still be up and it'll get uploaded as a video. So you can always go back into it. As in go back, as in make the video go back. I think you can place the cursor to where we started, even though we are here in the live. But you can rewind it. Thank you so much. Thank you, Kate.